Hello all, welcome to this presentation. This is Mohammed Amin. I am an associate professor with the Department of Electric Power Engineering at the Norwegian University of Science and Technology. This is the title of our paper, A Robust Synchronization Loop for Grid-Connected Distributed Generation Converters. The outline of this presentation is as follows. We know that the application of power electronics converter in the modern power system is increasingly used in renewable energy, high voltage direct current transmission system, FACS, in many other cases. And different control strategy such as the standard DQ control, the vector control, model predictive control, adaptive control can be adopted to regulate the power converter. Regardless of this control strategy employed in the converter, a synchronization unit is required. The synchronization unit that enables the converter to connect effectively to the grid. They provide accurate real-time phase information of the power grid for the robust synchronization of this converter. The synchronization is usually accomplished by detecting the phase of the grid voltage using a phase lock loop, for example. The PLL present a proper performance under a balanced voltage condition and also with a strong grid condition. PLLs are inherently nonlinear and sometimes it is difficult to tune for achieving satisfactory performance. And we also know that the performance of the PLL degrades significantly under unbalanced and distorted grid condition. Sometimes it also may introduce some instability problem. Knowing the limitation of the PLLs, so in this paper we are presenting a new phase tracking loop. I'm calling it a Robust-Synchronization-Loop for the grid connected converter to track the phase and frequency of the voltage for achieving robust synchronization. So first start with this modeling part. We know that before turning on this PWM of a converter, the converter voltage must be synchronized with the point of common coupling voltage. We must use the synchronization loop that track the phase and frequency of the point of common coupling. So based on that, we can reproduce the voltage. Here, what we are doing, we are assuming that we have our robust synchronization loop somewhere inside here, and we give input this voltage. This is the voltage of the point of common coupling. So based on this common coupling voltage, what it can do, it can give the frequency information and the phase information. So that is our purpose, to identify the phase and frequency using this robust synchronization loop. We give some feedback. We are assuming that this robust synchronization loop is producing the voltage E, whose frequency omega E and the phase theta E. So what we want, this E should be equal to the voltage V naught. Then it gives the frequency of the grid voltage and the phase of the grid voltage. So we provide some feedback signal from the estimated voltage. We are assuming that there's some error in the initially, since they might not be the same as both the voltage. So we feed this voltage error, this the E minus B naught, this voltage error through a virtual impedance. Here we have a virtual impedance. This virtual impedance give us some power. So what would be the power? And we can write the power like this way. So we have the power. This is the general equation of the power for this virtual current, and also we have this the voltage here. So what we see, in order to have it synchronized, we need to have the voltage of the synchronization loop equal. This is the magnitude should be equal, and the phase should be equal. So that's what we want. We want the same voltage magnitude and the same phase, and that give us the frequency and the phase information of the grid voltage. Then we can utilize this information for a robust connection of the converter to the grid. So what we see, we have a virtual impedance here, and we can decide what kind of virtual impedance we would like to have here. It could be either inductive or it could be dominantly resistive. We can decide based on our design. Here we are assuming it's an inductive impedance. If it's an inductive impedance, then we can get the power which is like this. We're assuming that the resistor is very small or negligible. So we got the virtual power equation, and since from this equation we see that the active power, which is related to the phase or frequency, this is the phase error between these two voltages, and the reactive power is related to the voltage magnitude. So we see two correlation between these two voltages. It's the active power with frequency and the reactive power with the voltage. So these two equations give us some hints how to estimate the frequency and the voltage. So first we introduce that the voltage, the frequency error is related to the active power. So this is the frequency error. This is the frequency error from the fundamental frequency that related to the power point of common coupling frequency, which is the summation of the fundamental frequency plus the frequency deviation. That's how we estimate this frequency. So this is the point of common coupling frequency that you can estimate, and how much the frequency deviation from the fundamental frequency, system frequency, that we can also estimate now here. So now we want to estimate the frequency using our synchronization loop. We are assuming that this is the frequency of the point of common coupling, and this is the estimated frequency. And there is some frequency deviation. We want to minimize we want to make this frequency deviation to 0. So in order to do that, we introduce an integrator here. We use an integral controller to make this frequency error to 0. So that's how we got this equation that gives us the phase error, and then we want to have the phase error to 0. So by combining the equation that we obtained in the previous slides for the frequency of the PCC and also this frequency error, then we can write the estimated frequency of the RSL is this one. Here omega naught, we put the value of the omega naught from the previous slide, and then we put it here, this part also, the del omega e, then we come to this equation. So now we see that we have this frequency of the RSL. We set this reference power, this active power, to 0. If we set this active power to 0, then we can combine these two gain together, then we can simplify it further. We know that in order to synchronize this voltage B naught with voltage E, what we need to have the voltage magnitude should be the same for both voltages. This is the one, and the second is the frequency, that is the phase of these two voltages should be the same. So this one we are getting the estimated frequency, and which should be the equal to 0. If we somehow regulate this power to 0, then we are getting the same frequency as the estimated frequency, as the common coupling frequency. So we got the equal frequency, we obtained the frequency that we need, and we set the magnitude of the PCC voltage directly to the controller, to the synchronization loop. What we do, we set in the DQ domain, DQ frame, and the magnitude of this RSL we set, which is the magnitude of this PCC voltage, and we put the EQ-axis voltage directly to 0. So now we have this the frequency, estimated frequency, and the estimated voltage magnitude. Now we inserted both of them. That give us this equation. One is for the frequency of the estimated voltage, and the phase of the estimated voltage. We also got the voltage magnitude, which we set equal to the magnitude of the PCC, and we can present in the block diagram. So what we see here, we have our input voltage. This is the PCC voltage, and this is the estimated voltage that our RSL, robust synchronization loop, estimated, and we feed it through the virtual impedance that give us this virtual current. And from this virtual current, we calculated the power with this. Then we get the power, and we know that this power has a linear relationship with the frequency. So that's give us the frequency of this robust synchronization loop. And we use this the phase angle to convert the ABCC beta into DQ frame signal. So that's how we develop our robust synchronization loop. Now we want to test it with a grid connected converter. We implemented this synchronization loop with a grid connected converter. I'll present some simulation result here. This is the first simulation result, an example I'm presenting. We can see that before synchronization enabled, there's a big phase difference. Here, this is the phase difference between the estimated voltage and the PCC voltage. We have not enabled the synchronization yet. And this is the voltage error between these two voltages. So at this point, here we see that there is a phase error around 50 degrees. So we enable our synchronization loop. When we enable the synchronization loop, and we see that this phase error is eventually going to 0 within some cycles, it goes to 0. And we can see it how it look like here. This is the phase voltage of the point of common coupling and the estimated voltage. And initially we see that there is some phase difference, and also that give us some magnitude difference. And when we enable this synchronization at this point, and we see that this phase difference is going to 0. So within some cycle, it can track the phase and frequency of the grid voltage. So that's how it works. So now we applied it through a power control converter. This is an example of the power control converter. So before starting the synchronization, and we see that the angle that it fit through, that give us some oscillatory behavior of the DQ axis voltage. This is the point of common coupling voltage, and we see that before synchronization enable, it's oscillatory. It's not a pure DC signal. And when we enable this synchronization, and we see that one of them, this D axis voltage, is a point of common coupling voltage, it becomes pure DC signal. And also the Q-axis voltage, it becomes 0. So we turn on our PWM converter, this power control converter at this point, and we set this power reference with the ramp rate, and it follows the current, and you see that the current is a pure DC signal. And we apply another step here. And how the power reference is following actually is given here. We put the reactive power to 0, but we set the active power. So what we see that at 1 second, when we set the active power reference to 15 kilowatt with a ramp rate, then it follows the reference power, and it gives us the 15 kilowatt, and it follows the reference. We see that with this synchronization loop, we can easily send the power to the grid. And another example is presented for change of the grid frequency. Here we change the grid frequency, is the 0.5 hertz. Initially grid frequency was 50 hertz, but we changed 0.5 hertz here. when you change the grid frequency, we see that the robust synchronization loop that we are presenting, it can track the frequency. And I'm also presenting another example of simulation for an unbalanced grid condition where we are sending the power P set and the Q set mode. This is the unbalanced grid condition. Now what we see that in this unbalanced condition, here at this point we keep this unbalanced condition for 0.5 second. We see that it still can track the phase and frequency. So now to conclude this work, what we see that here we are presenting a robust synchronization loop for grid connected converter to track the phase and frequency of the grid voltage. We presented detailed analytical model, and also in the paper we have presented method for tuning the parameters. So thank you for your attention, and if you have any question you can write to me